Terminal voltage. 5 resistors are connected to a battery with an EMF of 12 volts and an internal resistance of 1 ohm. What is the external resistance of the circuit? Calculate the current from the battery. What is the terminal voltage of the battery? Then calculate the power dissipation in the external circuit, and then the power dissipation in the internal resistance of the battery. What is the external resistance of the circuit? Well, the external resistance includes all the resistors except for the internal resistance within the battery. That's not a real resistor. That's just a measure of how much the EMF has been degraded over time inside the battery. So it's going to supply less voltage as time goes on. So let's start with R2 and R3 because they're perfectly in series, and that'll form R23. You just add them together, they're in series, and there they are. And we're showing a different way of doing our schematics here. I'd like to show different things so you can choose which one works for you or find something better. So we've redrawn the picture, so we've replaced these two guys with that. Now what do we have? We have these two resistors in perfect parallelism. So we will use the parallel circuit equivalent resistance formula, and we're going to notate that as the resistance of resistors 2, 3, and 4 is equal to, or actually 1 over that, is equal to 1 over the resistance, the equivalent resistance of 2 and 3, plus 1 over resistance 4. Put in our values, go to the least common denominator, and find out that R sub 234 is 2 ohms. And that's right here. So we've replaced now these two, where this guy replaced two other resistors, with one single equivalent resistance, R234. Now, we have 3 resistors in series, right? This is an equivalent resistance, but it acts just like real resistors. All we have to do is add them. They're in series. We now have the total external resistance of the circuit is 8 ohms, which of course does not include the 1 ohm internal resistance here. We can now calculate the current from the battery. It's just Ohm's law, where I is equal to the EMF divided by the external resistance here and the internal resistance here, because they're in series. So it's 12 volts divided by 8 plus 1 ohms, and we get 1.33 amps. Find the terminal voltage of the battery. We're going to use the terminal voltage equation, which is EMF minus the current through the battery times the internal resistance of the battery. So we have 12 minus the current that we just found times the internal resistance, and here's where the current is just to remind us, and we get a terminal voltage of 10.67 volts. Calculate the power dissipation in the external circuit. Once again, we'll use our power equation here, I squared R, but you could also use V squared over R as long as you're careful to use the terminal voltage and not the EMF. Only the terminal voltage is being applied to that resistance. But we'll use the first equation because that'll minimize our chances for error. We have the current, right? So we square the current times the external resistance, 1.33 squared times 8 ohms, and we get the external power. This is the power converted by the external resistances into thermal energy, 14.15 watts, and maybe light if it were a light bulb too. Calculate the power dissipation in the internal resistance of the battery. Now we're looking at this resistance. So it's the same current, 1.33 squared times 1 ohm, and we have 1.77 watts. That's power that is not available for use by the rest of the circuit. It's being consumed within the battery, which means the battery will probably warm up because of this, right? That energy has to go somewhere.